Welcome back to the fifth part of the series on Python for Astronomy. This part will deal with curve fitting and modeling of various astronomical models. So I will be using a new way of dealing with this today's lecture. So in today's session, since it requires a bit of explaining like some of the methods which you're going to follow, I will switch over to my notes section, and then we'll discuss it in further details. This is a bit of theory which the mathematical background is required for you to understand the concepts which we are trying to implement in today's tutorial. Okay. So this is just a hand waving explanation of what we're going to do today. But in case if you're interested in learning more about curve fitting and um, Bayesian analysis, yeah, just let us know in the comment section. We can make a further series on that in the future. Okay. So curve fitting. So curve fitting is basically finding the best relationship between the x and the y variables, or just finding the f of x. For example, you would have done this experiments in your labs where you had to find out the x and the y values. I mean, you have a control variable, you keep on changing it, and you get something which is a function of that variable, and you just plot it. And there are various kinds of plot. There are two types basically. They are linear or non-linear. The plot which I have here, this is just raw data, so these are just some x and y points which I just this is just raw data, just some data. So suppose I know that this plot, this relationship between y should be a linear relationship. Let's say it's like proportional to x. Okay, or I can just say that it's just a straight line, let's say. So if I know that it's a straight line, I mean, you can um, you can you can draw a straight line. Let's say it's something like this, or another possibility is like, I don't know, it could be anything. Okay, I'm not able to draw it properly, but yeah, I hope you get the point. Okay, so there are various possibilities. So now, which one should I go for? Should I go for this one, or I'm sorry, this one, or this one? These are two different lines which, by just inspection, just through your eyes, you can say that both of them more or less capture the the data, but the trend in the data, but which is the better fit, or which is the better line that represents this relationship? Is it the one first line or the second line? So there you need to have a sort of test, or sort of mathematical approach to finding which is the best curve, which is the best fit for this set of variables. So that's what we're gonna do today. And the most famous method, or the method basically to do this, is the least, at least for the linear case, even for the non-linear case. But I won't be discussing that in further details. But yeah, as I said, in the future sessions, maybe I can create videos for that as well. So what exactly is the least square fit, so called? Um, so the idea might look very simple to you, because so you first of all, you define a variable. It's also called chi-square. You will see why is it why both are same. Okay, so let's say you define something called chi-square, which is sigma I. Okay, so this is something which I find. So this is called the chi-square, or the residual. So you can see that So once I get a f of x, let's say it's something like m cap x plus c cap. Not that this m cap and this c cap is not, the exact slope or the exact intercept. It is some estimate which you got, and what you need to do is that at each and every xi, so if you're concentrating on the second part, like you have the point, and this is your y of I. So this is your y of I. Whereas for the pink line, it will for the given x of I, it will have a value of f of x of I. So there is a difference, right? So this difference is captured in this residual sum or the error. You can call this as epsilon I. Just write this as epsilon I square. Okay, so this is just your residual. So the best way of thinking about this is that the best line would be such a line that will reduce this chi-square or will minimize this chi-square. Okay, so yeah, so that is kind of the basic idea of least square fit. But you will be seeing a lot of different representation of the same formula. For example, you will be seeing like this is the formula. So this comes from a method called maximizing the likelihood function, which I'm not discussing right now. But yeah, that's the basic. I will keep session for that later maybe. So there is this extra guy which enters into the equation. This is your error in each and every point. So each and every point I can find the standard deviation sigma I, and I can plug that in as well to find the better estimate of chi-square. So once you have chi-square, actually you can try it out. You can take it as an exercise. So maybe you can try this, that why don't you fit for a straight line. So for a straight line, you know that let's just say that the y of I or sorry, the f of x of I is something like m cap xi plus b cap. Okay. So this is your f of x. Once you have your f of x, you can just find your chi-square. So your chi-square will be like sigma of epsilon I square, which is like sigma m cap xi plus b cap minus yi square. Okay. Now to minimize chi-square, you just need to take the derivative with respect to the variables m and b. So actually I shouldn't put chi here. That is when I substitute them. For example, you'll see it over here. So del chi square by del m, and put m and b cap which you got for the fit, and then put them equal to 0, and then del chi square by del b, and put m cap comma b cap equal to 0. So you have two equations here. Let's name it 3 and 4. So you just need to solve 3 and 4 and see what you get. So this will give you an estimate of m cap and b cap. Okay. So yeah, this is basics of least square fitting. Okay. Right. So there are further more examples which I could go for, but I'm just leaving that for some future videos. Right. Yeah, this is enough to understand today's tutorial. Okay. Now coming back to the Jupyter notebook. So yeah, you can code it up. You can actually find solve these two equations and find m and b, m hat and b hat, and write a code to find m hat and b hat. And then you can explicitly write a code to do that. You can choose any of your favorite programming language and just work it on your own as an exercise. But since we are doing Python here, which Python basically makes life more simple, because they already have a lot of modules in Python. So here we are talking about a particular function in the Scipy module called Scipy.optimize curve fit. So So this particular module actually deals with fitting the thing chi-square. So first of all, the least square fitting, the linear least square fitting, which we saw, works more better for a linear relationship. But what about non-linear curves? So for the case of non-linear curves, or for the case where you don't know how the noise behaves, so I should talk about that first, which I forgot. So we can only do this procedure where we work with finding the chi-square only when the data's noise we know is of the form of Gaussian or the normal form. If the noise forms is something else or which is unknown to us, then you cannot directly go with the chi-square or the least square fitting. There you have to minimize this guy, which is called the cost function, and there are various ways of uh, doing this. So for a data's noise which is not known, there are various algorithms which discusses it in great detail, and otherwise we're just fine with least square. Okay, so yeah, let's discuss Scipy.optimize. So first import the modules, and I I take some x data. This is my x-axis. Define a function. So this is just a quadratic function which I defined. And now I have to generate some function, the function. So here the function is like 5 minus x plus x square, which is your y. And now I will generate some errors in the function because I want to fit it. If I just generate a perfect function and then I just give it for fitting, then it's of no use, because it will give you the best values of a, b, c respectively. But I introduce some error. So here I am using the random normal distribution error, and I just add that error to the distribution. Okay, I'll just come to this x node later. Now so curve fit library contains some parameters which we need to discuss. Okay, so I'll just open this library, the description, so that you'll understand better. Okay, I'll just zoom in. So scipy.optimize.curveFit will take the function, which is exactly what I give here, func, then the x data, and then the y data, and this guy x naught or the p naught is the initial guess for the parameters. Okay, so here I have to fit for 3 parameters, a, b, and c. So my first guess is that they all are 0, which is just 0 function, 0 constant. So that is my initial guess. And also you can give some extra data, which is the error in the function, which is the uncertainty. So you can give that as a sigma. Okay, so this is your residuals which you can give. Yeah, so that is another thing which you can provide, which I'm not giving in this exercise, but yeah, you feel free to do that. So what does it return? So it returns 2 things. One is the optimal values for the parameters, and another is a covariance matrix. We will not go into the covariance matrix for now, but yeah, it's useful. It's useful to get that because we can describe the errors in the parameters using that. Okay, so I'll find a, b, and c. Just print it up. Okay, just run this again. Okay, so your a is some 5.66, but it was 5. The original value was 5. B is some minus 1.0, which is good, and C is some 0.99. Fine. Let's just plot it one over the other and see what happens. Yeah, this is a really good fit because it works perfectly for me. You can see there is more error in the fit, but this is the best fit. That's the most important point. So if you try to draw another quadratic function which almost fits over it, you'll see that this one is better than the other one because it minimizes the least square, minimizes the residuals. Okay, and so here you can look at the algorithm which they use. So yeah, so they use this non-linear least squares to fit a function. They use the non-linear thing to fit. And here you can see one more thing. With method LM, the algorithm uses the Levenberg method algorithm through least square. Note that this algorithm can only deal with unconstrained problems. So these are other sort of algorithms which you can put in the method option, so you can change the method here. Okay, but yeah, let's just keep it in default. So this is how you fit a curve in basic Python. But in astronomy, when you're dealing with astronomy problem, AstroPy, which is the module which we discussed in the fifth section, gives you an option which you can utilize, which you can make use of, which is the AstroPy.modeling. So AstroPy.modeling will have a lot of inbuilt models which you can just borrow and use it in your code. Okay. So if you look at it, so I'll explain this using some examples. First one is to add two Gaussians and create a spectral line. So a Gaussian distribution, how you know that it's just a normal distribution with some, it will have some mean and some standard deviation. And you will see that when you have two noisy Gaussian and you just add them up, you will see a sort of behavior which you can see in normal astronomy spectra, and you will try to fit one spectra at the end also. So this is the function AstroPy.modeling. From AstroPy.modeling we import models and see what it has. So if we just go to models and dot and see what it has, you can see a lot of stuff. Like you can see black body 1D, Chebyshev, which we'll see, and ellipse 2D, Gaussian 1D, Gaussian 2D, which we'll be using, Legendre, logarithmic, and so there is a Mexican hat 1D and 2D. So the models are various types which you can utilize for the code according to your needs. Here we are trying to use two Gaussian distribution, and it's one dimensional, so therefore I use Gaussian 1D. That's the thing which I'm going to use. If you look at it, you'll see that so it needs an amplitude, which is basically the scaling factor, and then the mean and the standard deviation. By default, mean is 0 and standard deviation is 1. These are the parameters which you need to make them. So you can see the param names are amplitude, mean, and standard deviation. Okay, and I'll just create first of all a model called Gaussian 1 with some amplitude 2.5, mean 0.9, and standard deviation 0.5. You can look at the parameters, and that's what you give. Now you can give the proper description of the model by just printing it. So you can go back here and just print Gaussian 1. Yeah, so this gives you the inputs, which is just X. I just need one input because one dimensional Gaussian distribution, and this is what you get. This is the amplitude, mean, and standard deviation. Now for the default case, I'm not giving anything here. So you'll see that the amplitude is 1, mean is 0, and standard deviation is 1, which we just saw. Once you define a default, you can always reset your parameters by just using this variable, your model. So Gaussian 2.amplitude, you change that to 1.6, change the mean to 1.8, whatever, and just you print it and see that it has been changed. Okay. Now we got the models. If you want, you can just plot them and see. For example, I just plot it up. Okay, I just take some x values, and then the y value will be the Gaussian 2x. Okay, and I'll see what happens when I plot them both to it. Okay, right, so the mean was 1.8, that's why. Let me just take some 5 to 5, minus 5 to 5. Right, so that's your peak, that's your Gaussian distribution. You can maybe plot y1, sorry, y2. Plot the first one as well. which was your Gaussian one. So that is so y1. Okay, so this is your y1, and the next one will be your y2. Okay, let this be in red color, whatever. So yeah, so you can see, so the amplitude for this guy was some 2.5. That's why this is huge compared to this. And yeah, so the mean and so now I want to introduce some noise to this, because in real life you won't get perfect Gaussian. You will always get with some noise. So the noise, I'll generate some Gaussian noise. You already saw how to generate some Gaussian random numbers using np.normal. Sorry, np.random.normal. np.random is the library. Yeah, so I declare a seed. So I hope you already saw the usefulness of declaring a particular seed. Yeah, it could be anything. So just declare random seed, and then data one is this guy, -5 to 5, some 200 points, and the noise is so normal function np.random.normal will take the mean and the standard deviation, and it will just draw from that distribution. So here it's 0 and 0.2 are the mean and standard deviation for the normal distribution respectively. We generate again 200 data points and just add them to the Gaussian data, and then I just plot them, and voila, this is what you get. You can see the Gaussian feature, but it's not clear because of the noise, right? Now I want to add them both and see what will it look like. Okay, I can also assign some names to this Gaussian line. For example, let me just take this as the main Gaussian line, and this is the second one, or the line Gaussian, whatever. Okay, and then I can just combine both the names. Both the models. So this is the combined Gaussian. So modeling library in Astropy supports this combination of two different models. Yeah, and you can see the submodel names and just print them, and see what you get when you combine the data which you found and the noise together. You see some feature like this. So this is a kind of spectra which you get, and if you look at it initially, which if you don't know that it's just made up of two Gaussians, you will see that you can actually see two peaks there, and we try to resolve them separately, and then we find out the mean and the standard deviation of each peak separately. Okay, so this is the two Gaussian model which we generated. This was the two Gaussian distribution underlining this, and we generated some noise as well. Okay, you can also separately do that. Instead of combining them here, you can actually add them separately and then do it. You'll get the same thing. Yeah, you can. Yeah, this is nothing. Just saying that both the methods will give you the same. Okay. Yeah, and we can look at the inputs. You just need one input, it will give you the one output. This is the combined Gaussian thing. So this is summary of the content. So you take one input, gives one input, and there are two components for this. One is a Gaussian 1D distribution with an amplitude 2.5 mean, blah blah, and there is a name associated with that as well. And these are the parameters: amplitude 0, amplitude 1, mean 0, mean 1, standard deviation 0, standard deviation, so on and so forth. You can combine as much modules as you want. You can combine two different types of modules. Two different types of models. Like you combine a Gaussian 1D with a Chebyshev polynomial or Legendre polynomial, and see what you get. Okay, now we'll try to fit the models which you generated with the fitting algorithm used by Astropy, not Scipy. We can also do it in Scipy. No worries there. But let's see Astropy's features, and let's see how Astropy helps in fitting better. So from Astropy.modeling, we import the fitting file. So this is the data. It looks something like this. Just the first peak. Okay. So this uses the LM method, LM optimization algorithm, which I was talking about earlier. I won't be explaining the way the algorithm works, but just take it as a fact that it is just like your least square algorithm, but for non-linear models. Okay. So the fitting algorithm which you use is this LMV Square Fitter. If you want to see the various kinds of algorithms which you have, you just go and check it out in the fitting command. You'll see a lot of different types. Like you have the simplex algorithm, you have the linear least square fit, and so yeah. So this is for the non-linear thing. That's why it's more effective, and hence we are using. So yeah, I defined it to a thing called fitter, and then this is my model. So the model was Gaussian 1D. So I generate a fitting model, which is the Gauss model. So because I want to fit a 1D Gaussian 1D distribution, that's why I'm calling this model. So this will go as the base model which I want to do, and this is my data, and data 1, which is this guy, and the x data, by the way, and the y data will be the g1 which we generated. X data, y data, and the model which you want to fit. That's it. So now if you look at the values of model, so model dot parameters give you three guys: 2.5, 0.8, 0.5. These are your amplitude, your mean, and the standard deviation respectively. The original parameters were 2.5, 0.9, 0.5. It's extremely close, which is good. Now let's try to plot it one over the other. You'll get something like this, which is perfectly fine. Okay. Now the fitting process has some extra stuffs which you can utilize when you write a code. Like you can constrain it. There is something called as a parameters constraint. You'll see three types of constraint: fixed, tied, and bounds. So fixed parameter means you can fix a particular parameter. Let's say you know exactly that the amplitude of this particular Gaussian distribution is fixed to, let's say, some 2.5 or some 5.2, some value, something like that. Then you can just write Gauss model dot amplitude dot fixed equal to true. This is a Boolean attribute, either true or false. That's it. And then you fit it. You see what you get. Just plot it. You see that it's fixed over the value 1, which is the default value, and hence it's constrained there. Okay. Similarly, you can keep a bound on the value. You can specify certain bound. So here I am keeping a bound on the standard deviation. The standard deviation minimum is 0.1, standard deviation maximum is 0.2. That is the bound for the standard deviation. So what happens when I put the bounds to this? Let's see. So yeah, when I put the bounds that the standard deviation should be between 0.1 and 0.2, it's awfully out of the context. But in many cases, when the algorithm can't fit it properly, then it's useful to give the bounds and to put some constraints. Okay. The third one is to tie different parameters. For example, here the three parameters are the amplitude, mean, and standard deviation. If at all you can find out some relationship between them, let's say the amplitude is some two times the mean or something like that, which you know of, then you can implement that in the thing. So here the model dot amplitude by 3.7 is so here we are saying that the standard deviation is tied to the amplitude, and standard deviation is like amplitude divided by 3.78. So the standard deviation, Gauss model dot standard deviation dot tied is equal to this function, which means it's tied to the model dot amplitude. Okay. Right now we'll plot it, and yeah, you can see it's much better because I've given it a constraint. We will utilize this function, this tying feature later when you want to tie different two parameters. Okay, so this is how we fit a Gaussian function. This is easy. Yeah, so Astronomy.modeling has several other features like simplex least square, linear least square, and so forth. Keep in mind, linear least square can be only used within linear models and provides you an exact solution, which I was discussing in the beginning. Now let's see another example using another model. This time I'm using a Chebyshev model. So Chebyshev model is like this. So you have it's just a polynomial with Chebyshev polynomial t of I with of some kind, and you have various coefficients and you just add them up. That's all. Okay, you can just look at it. Yeah, so this is what it is. So you will take the degree, which is the degree of the polynomial. You will have the um, various parameters, like, okay, you will just take the degrees, because yeah, you can also take this, guys, which is the domain, and the other parameters like the coefficients c0, z1, z2. So here I'm defining a degree 3 polynomial with these guys as a parameters. I add a Gaussian normal noise, and I plot it up, get something like this. Here I can use the linear least square because it's not perfectly non-linear, just a polynomial fitting, which you can always use linear least square for. And yeah, I use the linear least square fitter and then put the model, which is your chep1 and your data 1 and see data, and then you see what you get. This is your fitted thing and this is your data. It's good. It works perfectly here. Okay, now let's see an example. So here I'm going to fit an image of a disk galaxy with some model. So when you look at a galaxy, an image of galaxy through a telescope, optical telescope, you'll see that it's it's surrounded by a lot of noise. I want to develop a model for the galaxy which I can fit it, and then I can just subtract out the noise from it. Okay. First of all, I'll have to create a example data set. So most of the galaxies look like a 2D Gaussian distribution. The center will be a really bright source, and then it will just fade off two-dimensional Gaussian distribution style. Therefore, that's the model which I'll be using. So I want to first of all generate a noise for the sky. So this is my sky. So the sky is np dot random dot normal, and this is the 128 cross 128 grid distribution which I generated. Same thing, I generate x and y for the fuzzy galaxy model. For the galaxy model, I'm using Gaussian 2D with some amplitude x mean, y mean, x standard deviation, y standard deviation, and some angle of inclination, the theta, for because otherwise it will just look perfectly like a circle shape. I want it to be inclined with some angle. That's why I'm putting the theta thing, and then I just multiply it several folds so that the galaxy will stand out in the noise. Then I just add both to combine both the galaxy, fuzzy galaxy, and the noisy background to get the image which I need. And this is what it looks like. Okay, you can see the noise. Also, you can see the galaxy. This is kind of the image you get from a telescope. Now let's try to model this galaxy and then subtract the noise out of it. To model it, I use another fitter. This time I'm using the Lml Square Fitter. So that's what I use. I have to fit both the sky and the galaxy separately. So for the sky background, I'll generate a constant distribution, uniform distribution, two-dimensional, and the uniform value will be set to the median of the image. So I'll find the median of the image, okay, and then I'll fix that as the amplitude for the sky model, and then that is basically the noise. Now I model the noise. Okay. To model the galaxy, again I use two-dimensional because that's what I created the galaxy with. But suppose if you don't know that, the best guess is that this distribution looks like two-dimensional Gaussian distribution to me. That's the first approximation which you do. So the amplitude is 0, initial thing, which is mean and median. You can see that it's around, the x mean and the y mean somewhere around 55. Standard deviation some values, and theta values you put a constraint. So yeah, you can put the constraint as 0 to 2 pi, because I know that angle is between 0 to 2 pi. Otherwise, again, you get back some 2 pi plus theta, you get back your theta back. It's of noise. So I have to constrain theta here. That's why I constrain the theta values here. Then I create the scene, which is the sky model plus the galaxy model. That's a compound model now, just like you are doing the compound model for two Gaussian system. Now just fit them using the scene, X, Y, and image. Okay, so again, this is the compound model. And now I just need to plot. So I'm plotting subplot of the image. This is the image, the model, and image minus model. They're different. This is the noise. So the noise and the image. So it looks perfectly modeled. So this is the model distribution, and the different. This looks very neat because I knew, because this was a synthetic data, right? This is something which you developed. So you had a model, something similar to this. You just added noise to that, and you get image. You just went back from the nose to back, circling this forehead, and came back to the nose again. That's what you did here. You just you had a simulated data, and you did your fitting or the modeling using the simulated data. But in most cases, you don't simulate your data. It's something which you get from an experiment or just an observation. That's what we're going to do next. So in that case, how do we tackle that problem? So here we are doing a problem on fitting a spectral line. I have a code called sample sdss.txt, which is a spectra from SDSS survey, SDSS data set. Just need to import it. You can always use numpy's loadtext command to import, but since I'm already dealing with AstroPy, and AstroPy has a import command called ASCII, I'm using AstroPy's ASCII command to read the text file. You'll see that it has three column names: lambda, flux, error, temperature. The lambda value or the wavelength, that's the first column, is just the wavelength, which will be your x-axis. Remember, I'm going to plot the spectra of a star or whatever. So you'll have a wavelength in the x-axis and the flux in the y-axis. So that is your flux, and there is an error term. Okay. So now I see what it gives me. So you can see a lot of peaks. Each of them are actually Gaussian peaks. They have some mean and some standard deviation associated with it. And these are some lines which immediately you can't see, but there are some lines to this. So to find them out, I will explicitly declare them. So these are the separate lines of various elements. For example, the H beta line, H alpha line, oxygen 3 line. Oxygen 3 line occurs in doublet. That's why I'm giving 1 and 2. Sodium line, and so on. Okay, so I just declare them first of all, and then plot them one over the other. You can see that okay, this is just out. Just okay. I'll put this as 175. What happened? Okay, missed a comma. Right, so you can see this is the H beta line. This is the O3's first line and second line, because that was a doublet. H alpha line, and there is again SA and SB here. There is no sodium here so far. So these are the lines which I want to fit. Let's try to fit H beta and the oxygen doublets or 3 doublets. So to fit this, so there are two things here. First of all, there is a resident, there is a background to this, or wait, just a second. So I can put full screen. Why did I think of that? Okay. So there is a background to this which I can model. I have to model that background plus these 3 peaks. corresponding to the H beta line, O31 line, and the O32 line. Okay. So first of all, I need to model that background, which is just like a polynomial. That's all. I just need to find the best polynomial that could fit this background, as you can see. So to fit the background, I am actually trying to find the best way to model the continuum. So I model the continuum like this. So wherever there is the flux which is greater than the mean flux, I use the condition that it will be just the mean flux. Otherwise, it's just the flux. So there is a mean flux to this. So the mean flux is here something like 1.8 or something, somewhere over here. That's your continuum, and whatever happens below that is fine. But uh, uh, and above that, I don't want anything else. So my continuum should be there. That's it. So I will model it like that. So when I plot the wave, when I plot the continuum, look something like this. Okay, you can see wherever it's lesser than 1.8, it goes below negative. That's fine. But if anything is more than that, I'll restrict it to the mean so that I can subtract it out while modeling the peaks. Okay, that's the main reason why we are modeling the continuum. Then I fit with the polynomial fit. This is what I get. Okay. I model the continuum. Fine. Now let's model the three Gaussian distribution. Each of them are separate one-dimensional distribution. I can just look at it and find the mean values. These are the mean values which I can find. Okay. These are some guess, and I can also guess the amplitude from the y thing. So I just guess them out first. These are the guess values. Standard deviation also, I'm just giving the guess value of 5. And mean is the mean of H beta, O31 and O32 respectively. Then I combine them. Sorry, I didn't run this. I combine them to give a compound model. Okay. Now comes an interesting thing. I can directly plot it and see. I can directly fit it and see, but you can actually constrain several variables here, because I know the intensity, the ratio of intensity between two O3 lines, which comes from the theory basically, which comes from the spectroscopy theory. Also, I can tie the wavelength of the beta line to the oxygen 3 lines wavelength, because they are accurately known to us. You can put that as a constraint as well. As much as possible, you need to find constraint when you are modeling such nonlinear functions. So here my first constraint is this thing, that I have the ratio of intensity of two thing. So that is the amplitude 1. I am tying with this amplitude 2. Similarly, I can combine the mean of 0, which is the mean of the H beta, wavelength of the H beta line, to that of the oxygen line. Okay, so define two tie-ins. Then I call my nonlinear square fit LM method, and then I just fit it. This is what I get. So you have the continuum which I model. I also get the peaks here corresponding to oxygen 3132. This is a really good plot. Okay. So yeah, this is the final plot. This is how we fit a perfect spectrum. Fitting spectral lens. This is your wavelength, angstrom units, and this is the flux. Okay, you can play around with it and save it if you want. Right, so yeah, maybe you can zoom it a bit and see what happens in this region. Let's put the limit on x. Let's say 4,600 to 5,500. I can limit it further. Yeah, you can see them. Yeah, you can see, you couldn't notice this difference when you were seeing from the full picture, but you can see that if you knew the if you had a better constraint for the amplitude, you might have got a better graph, I guess. Maybe we can tweak that and see. Also, you can tweak this amplitude as well, but more or less it looks fine. It might be due to the fact that at this point you have a bigger noise fluctuation. Otherwise it's fine. So yeah, this is how you model a spectral line. Okay. Yeah, so that was this tutorial. So it was basically you learned about modeling various curves and fitting various curves and fitting various models in astronomy. You learned the least square method as well. Okay. As an exercise, you can try maybe to try to model the remaining spectral lines, for example, like H alpha and SA and SP. Try it on your own and see what you get. Okay. Yeah, and just comment down below if you are interested in having a separate session where I discuss the various algorithms related to fitting and maybe a series on Bayesian astronomy and Bayesian curve fitting itself. Okay, bye. I'll see you in the next part.